Okay, everybody, I think it's 10 o'clock, so I'm going to get started. So we're talking about the Wolfram Compiler this morning. We've actually got, there's the talk I'm giving, this talk goes from now until 11 o'clock, and then there's another talk from 11 to 11:30. We're fitting in a few different people, so I'm going to talk for about 45 minutes, and then some of the other team, a group of us that work on the compiler, we're going to be talking. Brenton will join into my talk. We'll finish that at 11 o'clock with a sort of summary, and then we'll start another talk on the compiler with Abdul, and I might wrap up with some more material. We won't be taking any questions at the end of this first talk. We'll save all the questions for the end, or we could carry over to lunch, because there's quite a lot to talk about. Right. Now, so this is the Wolfram Compiler. It's a new technology to enhance the core of the Wolfram language, and we're going to be looking over this. This is a long-term project. I've been talking about this I've been talking about compilation in general of Wolfram language for many years, but this particular project, I've been showing you advances in this over the past few years. It's a long-term project. Eventually, it's going to replace the old compiler with a completely new implementation, and it's built in the Wolfram language. But I'm pleased to say, I hope this is, there's an initial version. The first release of the compiler is going to be included in version 12, and I'm using a version 12 right now. So there's definitely going to be some rough edges and some things not quite finished, but we believe that we've got something that's useful and powerful and a thing to move forwards with. So I'm going to look at general features of the compiler, some of the internals, and then I'll be looking, and Brenton and Abdul will also be looking at some examples of interesting programs that we can write with the compiler. Now, who is interested in a Wolfram compiler or a compiler for the Wolfram language? Different sorts of people. The one set of person. Sorry, did I? Oh, everybody. Right, fine, good, fantastic. Right. I'm just trying to set the scene to say what are motivations. So there's just ordinary users, ordinary in a general sense of Wolfram engines and things, and they're going to benefit with just automatic compilation through functions like plot or such like. And as we move forwards, we can start to rework a lot of existing features like the pattern matcher or library link and things like that. We can rework with our compiler technology. So another category of person is people who actually use the compiler. A lot of people I know that come to a conference such as this, they try to use compile in their programs to try to make things faster, and they're willing to do some tweaking and such like to make things conform. I think now, moving forwards, there's another category, going on from that, and that's the people who might be interested in sort of extending the compiler, and there are ways of extending it, of adding new data types and adding libraries and special optimizations. So I think that's quite interesting. The compiler has a lot of potential for integrating with other languages. So people who are not necessarily interested in compilation of the Wolfram language, they want to integrate other things into other languages, other technologies into Wolfram language. And it has a lot of potential for that. And a last set of people is developers and researchers. And I think that people doing research in CS departments and such like, I think this is a great technology for developing new special optimizations, proving things, leveraging some of the technology behind compilation systems. And so I think there's some potential here. Right. Now, let's just dive in. This is the main, this is what Stephen showed. The sort of main initial way to use the compiler is there's a new thing called function compile. So it's different syntax, and function compile takes a function, a pure function, and it returns an optimized sort of, a compiled code function that will execute your function. Now, if you give it some, different, something that's not, you get an error. So this is supposed to be integers, 2 integers. I gave it a Boolean. You get an error if you do the wrong thing. So what's supported? So core native types, integers, reals, complex packed arrays. But we're also supporting different sizes, like unsigned integer 8 and real 32. These sorts of things, they're actually manifest in numeric array, which is a new feature coming out in version 12. There are some talks on numeric array. They're also useful for like machine learning. Often wants to solves problems using smaller floating point sizes. So we support many standard programming features, nested functions closures. Errors are propagated with hardware exceptions. So we try to make a very modern language implementation, a variety of output targets, and we have a documented official callback mechanism to the Wolfram evaluator for things that don't currently fit in, a fallback, a bridge for things that don't currently fit into the compiler. So just go through some of the types that we're supporting. We have, I don't want to be too technical in this, but we're supporting, a bunch of atomic types. Well, maybe complex isn't really an atomic type, but it's there. So we have things like that. Compound types. So packed array is the sort of initial version. So you have a packed array is a type, but it's a type that takes other types to sort of, become useful. And so this is a packed array, and it's being given an integer 64, and this is like a type literal. So this is like a dependent type, and this is saying it's a vector, and this here is a complex real 64. This is a packed array of real complex numbers, and it has 2 integers, so it's a matrix. So that's that. So we have a function type. So you can see the function type. A little bit small there, but it's like, T1. Yes. Sorry? I don't know how to. Yeah, I don't know how to zoom that. Sorry. I'm using some style sheet and the zoom button. I don't have a zoom button, so sorry. Move to the front. Right, this is a function type, and it's specified with a list and a rule. So these are the arguments, and this is the output. That's function type. And then we have more other internal types integrating with C and C++ libraries. We also have a polymorphic, which is a quantifier type. We're probably not documenting that in version 1, but internally we use it a lot. So packed array support.
Try and go to window and then magnification. And then say yeah.
Oh, there we go. Right, there we go. Now I do know how to do it. Right. So this is I've got a function, and it's being given a packed array of reals, and I'm applying fold. So I'm doing a fold operation, and this is the, it's just like some marching down through the packed array, applying a function to it. So that's. Now, here's a way that the compiler is completely different and more advanced than the old compiler, and that's the way that it deals with nested sort of inner functions. And I'm going to show you some sort of internal, this is our sort of intermediate code that we compile into as part of the compilation process. So we have here, I've got like an inner function, and that's held as a variable, and then I'm applying it to an argument. So all I have to give is, for type inferencing, the type of the input, and everything else gets figured out what happens. And we can use these. Here I can, we have very good just natural support for this. So I can use these functions as data. So I've got a condition, and I can say, depending on the condition, it's this one or this one that gets applied. I can have, like, here I've got a function. So this is a function that returns a function. And, we can see, so here we've got the type of this. So this is a function. It takes no arguments, but it returns a function. So we have functions that return functions. We can have functions. I mean, you just sort of carry on sort of arbitrarily with this. Here's a function. We pass a function in, and then we pass it as an argument, and it comes back, and this all works. Now, this might sound, a bit exotic, but actually, it's actually quite powerful, and this is new to our compiler. Another new technology that we've added is support for what you might call closure variables. So here I've got some inner nested function, and this is referring to a local variable that comes higher up in another function that's wrapped around it. This is called a closure variable, and we support this. Now this sounds abstract, but it's actually very useful, not least as a way of encapsulation. This is a way of correctly dealing with global data, and I'll show some good examples of this later in my talk. So, yet another thing that we can support using this mechanism, we can support recursive definitions of functions. This might be a bit hard to read, but so I'm using module to get recursive definitions. Now, really, I'd rather use with, but we don't have a recursive version of with. This is like in other languages have a thing called let rec. We don't have a construct like that, but I'm using module for this. So here I've got a function, and called factfun, and in factfun I'm referring to itself. Now this is maybe I shouldn't talk about this because most people aren't interested in it, but this is in the theory of lambda calculus. Such things, these let rec constructs are actually created by these W or Y combinators, depending upon what sort of language you're working with. And it's one of the wonders of the world that such things, that you can implement recursion without having to give functions names. So this is really just syntax sugar for these combinators. Now, what's also very satisfactory is that I'm compiling this down. The only type I've given is the input type. I've got a recursive function, but it's able to give the type inferencing system is able to determine the type of the whole thing, and so I can generate executable code that works. And I think we were pretty pleased when we got that to work. Now, again, all of this sounds a bit academic, but it is not. It's quite profound, and it's in the modern world, this is a much more modern way of programming, and it's like I said, it's an important way to encapsulate data. It allows you to build. This is a lot of the benefit of modern languages that have lambda, like JavaScript, for example, and it allows you to build up a style of programming that's similar to sort of the old, class object-oriented style. It's sort of equivalent to that, but it's much more modern and powerful for various technical reasons. And also, I might say, passing these functions is essential. See, we can essential for any sort of parallel operations. That's just goes without saying. Now, let's look at some other features. Variety of different outputs are possible. So here I've got, this is like we do function compile, and we get this compiled code function coming back, which executes. Now, if we have a look at this, at the input form, we've got, this is the compiled code function. We've got some sort of metadata here, and then we've got some numbers here. These are actually function addresses. So it's compiled this down to machine code that's loaded into the environment, and we can talk about how this is done. But this is actually executing native assembler code, just as if you wrote a C program and invoked a C compiler and made an executable. But it's doing this sort of dynamically as we request it. And so this means that the default way of operating is entirely the same as the old compilation target goes to C, which I know, at least some of you were used to make use of this. So how does this work? We use this thing called LLVM, and that's this underlying technology. And LLVM has this intermediate representation that's like a platform-dependent assembler. And so here I've got a function that I can see here, and it's got, we've got two functions here. This is the main function here, and then this is this sort of inner function that's in here. And we can talk about, if anyone's interested in the structure of this, it's written in this form. All of our intermediate code is written in this compiler form that we call single static assignment, and that is, it has this interesting property. It's a little bit like a lambda calculus form that's sort of folded inside out, and that's how modern compilers do things. Anyway, so we can generate this intermediate form, and then we can also go one stage further and generate actual assembler. So this is the assembler for that function. So we've got various calls to runtime libraries and jumps, and it's calling functions and things. So this is getting closer to what's actually executed. Now we have a target system option, so I can generate. What happened there? Maybe I didn't do. There we go. And this is generated. There we go. And this is, we can change this to, other, native assembler for other platforms, and I generate this WebAssembly stuff. And this is this sort of assembler that executes in browsers. That's kind of interesting. Hopefully, something we'll be able to make use of in our cloud products. We can also use function compile export. We can write into a file. So I can write this. This is basically an object file. So we can look at this. Looks a bit boring, but this is an object file. This is what your C compiler produces. You could link to this with a C program or a C+ program, and it would execute. And again, we've got the same target system options. One of the good things about LLVM is it's quite cross-platform, so you could, compile code on one platform for another if you were interested. So another feature we support is generating a shared library. So now I've taken the function here, and I'm writing it into a library. Now this library, I can load it in, and I get a compiled code function that I can use. So one benefit of this is I don't need to recompile the code every time. I can just make this compiled code this library and load it in with library function load and use it each time. Another benefit, I could link to this library from external code as well, which is also useful. Now, so other backends, keep an eye on the time. There's a whole load of backends. Some of these backends that we're developing don't use LLVM at all. This is one where we have our own intermediate code, and then we turn it into a C program. So this is not involving LLVM. This is just going straight from our code into C. So that's kind of a nice way. You see, in the old compiler, what we did was we had our bytecode, we would generate C, and then we would compile that. But what we're doing is we're going in the opposite way. We have our compiled code, we're generating our bytecode, and then we can either convert that into assembler or we convert that into C code. So that's. But actually generating the C code, it's not so useful because you can just make a library. Now, one of the things that people have long thought about with the compiler is, they always worry what can be compiled, what can't be, and that's kind of an issue. And we've added a mechanism to, work with the native evaluator internals of the Wolfram engine. And so we can, there's a type. This is more of an internal thing, but I'll just show you roughly that. So we can make a function, and we can give the arguments the type expression. And this is going to work for numbers. It'll work for big numbers. So these are not machine numbers. It'll work for symbolic types of things. So this is, using the sort of internal Wolfram expression mechanism. It comes with a price because it's not very standalone. It's tied to the Wolfram engine. Now we've used this to implement this thing called kernel function. And the kernel function is a bridge between evaluated and compiled code. So here, in fact, we have support for, that I'll talk about in a bit, for things like Bessel function. But supposing there's some function that's not supported, you don't think supported, we've added, so you add a kernel function for it, and you give it a type, and you pass in the arguments. And so you do this, and then this is going to be your, type of thing. So that's they're the same answer. So this is a way of integrating evaluator code in compiler, which I think is kind of useful. And you can use the kernel function. You can also give it a pure function. It just has to be a function, and it has to meet this signature. And you can also use the kernel function as a function object that gets passed around. So you can use the same, quite useful if you want to do the same thing many times. You can just give it a name and then refer to it in a bunch of different ways. So here I've got this function, and depending, I'm applying it to different arguments in my program. And you can also have this kernel function can itself return a function. So I've got an example here. I've got another example that I kind of like here. This is a bit sort of complicated, but there's many things in the Wolfram language, like ndsolve, that itself returns a function, and so ndsolve returns an interpolating function. So here I've got an ndsolve, and that's returning, so the interpolating function, so I can solve a differential equation once, and then I can use the interpolating function that comes back multiple times in my compiled code. And I think this is kind of a nice integration with the system. So we'll kind of run this, and right, so this is the, what have we got here? This is the initial condition. So, and this is, I'm trying to think, what am I doing? I'm evaluating this at the, right, this is the initial condition. Sorry, this is the initial condition, and this is the value of t. So not surprising, when I evaluate the thing at the first point, I get back the initial condition. So that's, and it, it's really calling the, this is going up to 30. So if I was to make this, 200, then I would get the interpolating function, sort of error that comes out, because that's, and so this is pretty useful. So the kernel function is an extension mechanism where we don't have native compiled code. So, yeah, doing okay? Right, so I'll just talk now a little bit about the compiler pipeline that we have. So we start with, the Wolfram language, function, programs, and we go through various steps as a tree. We generate this intermediate code. We do type inferencing. We resolve, do linking of functions and such like, and then we generate an executable. So here, for example, I'm generating the intermediate, untyped intermediate code. So there's no type. I haven't given any type annotations, and I've just got generic names for these functions. So we can do type inferencing on this. So now I've figured out that times of 2 integers returns an integer, and so does sort of plus, and then that's the result. But I haven't said which plus. And then the final thing is I resolve function calls, and now I specialize, generates more code, but I've specialized the plus to a particular the times to a particular times that works for sort of in integers and such like. And then the final stage is to do cogeneration and come up with a compiled code function. Now, again, a lot of the internals of is we have all these passes that do all sorts of different, this is how we implement the compile. We have all these passes that do, some of these do optimizations, fusing basic blocks and removing redundant code and jumps and things. Right. So the compiler's built on top of this LLVM technology. So a lot of people haven't really heard of, some people have, some people haven't. So LLVM is evolving as the standard technology for compiler, or one of the very leading structure compiler infrastructures. It's the basis of the Clang C and C++ compilers, but it has a lot of support from, on Apple use it, and Microsoft are using it, and IBM, and many companies, when they want to do some sort of, NVIDIA, when they want to do some things, they base their tools around LLVM, and we're able to use it. And there's a lot of work that we get a lot of benefits from that. Right. Talk a little bit about the type framework. So the type framework is the idea. So we have a static typing. We give type annotations, typically on the exterior input to functions, and then we do inferencing, so we can determine types throughout the function, and that means you don't have to put type annotations in lots of places. Makes it quite convenient. We also support a thing called parametric polymorphism, and that means that, I'll explain a little bit what that is. A little bit of code can go a long way. And the type system actually is independent of the compiler. So it has no dependency on the compiler. The compiler uses it, but not the other way around. Type theory is also, it's quite tied to, there's this correspondence between compiler type theory and the math and logic, mathematical logic, and there's a relation that's somewhat similar to sort of type theory of doing theorem proving, and there's people at Wolfram Research that do work in theorem proving. Theorem proving is kind of like the opposite direction. So in theorem proving, I think you start with a type, and that's kind of your theorem, and if you can find a lambda function that has that type, that's equivalent to a proof of your theorem. We, in the computer science world, we do the much easier task is we start with a program, we start with essentially a lambda function, and then we figure out what its type is. Is it well typed, and what is the type? So that's kind of like the forward problem. As you know, inverse problems are harder than forward problems. Like integration is harder than differentiation. So we have the easy direction. Now, let's just have a little talk about polymorphism. This is how we write a lot of our code internally. I've written here a function. So it takes a packed array, and it's it's basically adding up all the parts. This is like total. Now, I've written it here, but I could write another version, like say with real 64. So the program, all I've had to change is the type. The rest of the program is the same. Wouldn't it be nice if I didn't have to sort of, cut and paste all these names? And yes, it would be. That's why a polymorphic. So here, I've written the function. I've not given it any type signatures. What I'm using here is a quantifier. So this is the same as a quantifier in logic, or in here, I'm giving it a type variable. So this is saying it's going to work for a packed array, but I haven't said what sort of packed array is it. It's a packed array of something, and that something is going to be the output. So let's enter that. Now this is slightly sort of, we're still figuring out so I'm adding this function here that I've defined. I'm going to add it to the system, and then I've got a function here that's calling it. So I can do that, and now I can, my function executes, and it works for, sort of, an integer. But what's kind of nice is this function is defined polymorphically. So here, I'm going to feed it to a packed array of reals. And the inferencing system does figures all that out. And so now this version of the function works for real numbers. So this means a little bit of code goes a long way. So that's quite useful. And in these quantifiers, we kind of have an elaborate language. This is a simple case, but you can put constraints on these variables that have to be met in order for the type to work. Now, right, talk about some programming examples. So one of the things that we want to use this compiler for is for programming, and I want to try and give some idea of its potential. So one of the things I want to do, in fact, I gave a talk at Microsoft Research in Cambridge in England earlier in the year, and some guy at the back put his hand up and he had some questions about Quicksort. It turned out it was Tony Hoare, who was the original developer of Quicksort. So I'm very sorry, I don't have. So then I thought, right, let's do Quicksort. That would be. And so Quicksort, it's quite a good algorithm because it's representative of a big class of problem solving because it uses a strategy called divide and conquer. So in Quicksort, I've tried to sketch this out. What you do is you partition, you're sorting your data, you partition it somehow into two halves, and then you work on, so here's your partition function. You do the partition, and then you do the sorting on, the low side and the high side, and you keep doing that. And this is a good. This has good. This is going to work efficiently. It's divide and conquer. Typically, it has like an n log n sort of property. Now, so here's the implementation. I'm not necessarily asking you to read all of this, except we're using these closures, we're using recursive functions, but this is a quicksort that we can implement. Now, I can actually, that same function, I can give it to a, it's the uncompiled version works. But let's come and compile it. So we compile the function, we generate a compiled version of this, and there we go, and then we apply it, it also sorts. Now the advantage that we've got is we've made this faster. So here I've got 10 to the 5, and this is the uncompiled version, which takes a little bit of time. There we go, 6.5 seconds, and this is the compiled version. So we've got a very significant speed up of timings. Now, you might say there's a built-in sort in Mathematica, and you're right, there is a built-in sort. So how does that compare? Let's do a bigger version. So this is my compiled version. That took 1 second, and this is the built-in sort. So that's quite a bit faster. Now, let me assure you, the built-in sort is not 20 lines of code. It's hundreds of lines of code. This quicksort is very, very simplistic. Usually when you're sorting, you do divide and conquer down to some size, and then you switch strategies, etc. So I'm not totally disheartened about that. But just to prove I'm really not disheartened, I'm going to cheat a little bit. So now I'm going to do something that's a little bit more like the internal version of Quicksort. Because what that does is it doesn't work on the sort of packed array thing. It takes the data out of the packed arrays, and it works on that. Well, we can do that in the compiled function. So we're doing this. We're getting the raw data, and then we're going to operate on that. So now, this won't work in the evaluator, but we can compile this, and there we go, and we apply it, and this works. So now when we compare this with the hand-coded version, so this is the compiled version, and this is the, so now we've got down, we're still a little bit slower than the 0.22. We're, factor of 1.5. But I think factor of 1.5 to come to carefully, Mark might be here somewhere, or Rob, whoever wrote the sorting, actually it's a merge sort in Quicksort is just like less lines of code, and Tony Hoare asked about Quicksort. But I think that's pretty cool that we can write in 20 lines of code something that gets within, as fast as that with carefully handwritten C code. So I think that's kind of exciting. Now, really what we want to do is, we had to cheat a bit here. What we really need to do is to take the generic packed array version and add optimizations to it to turn that into this. And that's totally practical for us to be able to have optimizations do that. But, oh yeah, absolutely. But since we could, yeah, Quicksort lends itself to parallelism very nicely, and having, this sort of access to, make it simple to write code means you can write complicated code without pulling your hair out or jumping off a cliff or something, And Wolfram language programmers have never been able to write fast code like this for common algorithms. So I think that's quite exciting. Yes, we have built-in sort, but sort is, there are like PhDs on PhDs that people, sorting is such a core fundamental thing. I think it's exciting that we can work with that. Now, I'm going to halt now and switch gears to Brenton, who's going to show you some work that he's been working on. So don't go away.